Hello, welcome to Key in Motion's course on understanding electricity and electronic devices. In today's class, we're going to study voltage regulator ICs or integrated circuits. More in detail, the content of today's class is going to touch voltage regulator integrated circuits in two categories, which are fixed and variable. And we're going to go over some power calculations and we're going to look at a few parameters of these integrated circuits and see how they perform in different applications. Okay, so if you recall from previous classes, we looked at simple Zener diode regulators, and we saw that their performance was not very good. They were useful for limiting the voltage to another device in an interface circuit, but by themselves, they were not very good as voltage regulators. We also saw that performance can be improved by adding some more components around the basic regulator with a resistor and a Zener diode. And the circuit that we saw was adding one transistor. There are other improvements that can be done over there with amplifiers and stuff. But the good thing is that some semiconductor manufacturers put all those good circuits, all those improvements to the Zener diode regulators in a single package. And that's what we generically call a 3-terminal voltage regulator. Okay, and this is what we're going to be seeing in this class. Probably the most popular and one of the oldest series of voltage regulators is the 78 series. These voltage regulators are integrated circuits that are known by their part number, which is 78 followed by the voltage, right? So, for instance, 7805 is a 5-volt regulator, 7812 is a 12-volt regulator. These devices look like this, right? They have 3 terminals, as you can see here, and one is input, then an output, and a connection to ground. And for optimum performance, they require just one capacitor at the input and one capacitor at the output. But for most cases, those 2 capacitors are not even required. So you have a complete voltage regulator solution in a single package like this one. Okay. So let's have a look at the typical performance of a 7805. So a 7805 accepts an input voltage ranging from 7.5 volts to 35 volts and can deliver a maximum output current of 1.5 amps. And the line or load regulations are 50 millivolts or 0.05 volts. Line and load regulation is how much the output voltage varies when the line voltage or input voltage varies within the specified range and whenever the load current varies from 0 to the maximum specified current. So as you can see, this regulator accommodates a very wide variety of input voltages and a very, very decent range of output currents from 0 to 1.5 amps. And it maintains the output within 50 millivolts. So it's very, very good performance there. There are also adjustable regulators or adjustable versions of the 3-terminal regulators. And one example is the LM317. The LM317 is used and connected like this. You have an input voltage, you have an adjustable or an adjust terminal and an output terminal. And you put this voltage divider here between the output and the adjust terminal, and you can control the output voltage by this equation, right? So the output voltage is going to be 1.25 volts times 1 plus R2 over R1. So if R1 is fixed at 1.2 kilo ohms, as we have the case here, and we make R2 variable from 0 to 20 kilo ohms, when R2 is 0, your output voltage is 1.25 volts. So that is the minimum output voltage that, that you can get from this regulator. The maximum voltage that you can get from this circuit is, well, when you put the values of R2, 20 kilo ohms here, you will end up with something closer to 20 volts. And this is only because of this circuit, right? So you could use a higher resistor here and get even higher voltages. The input voltage has to be at least 3 volts above the maximum output voltage that you want to obtain here. And I don't remember exactly what's the maximum input to output voltage difference, but I would expect that to be around 30 volts, okay? So you could adjust these for 12 volts in the output and have as much as 42 volts on the input, and that will work just fine, okay? Let's do some calculations about power dissipation because this is important, okay? Remember, any wasted power in the regulator transforms into heat. So any power that is not delivered to the load, it's gonna be heating up the regulator, and there's a limit of how hot this can get. If we want to calculate the power dissipated on the regulator, we can calculate it as the difference as the input power, so the power delivered to this whole circuit, minus the power delivered to the load, which is the power delivered to this part of the circuit, okay? So the power delivered to this whole circuit is gonna be the input voltage times the input current, right? And the output power delivered to the load is going to be the output voltage times the output current. And the power on the regulator is going to be the difference of these two. Now, the input current is usually going to be very close to the output current, because the current that goes through the ground terminal is very low, okay? So this current could be a few milliamps, but this is gonna be maybe like 1 amp or 1.5 amps, okay? So if we assume that no current goes through the ground terminal, we can calculate approximately the power dissipated on the regulator as the voltage difference times the output current. Usually these voltage regulators cannot handle more than 5 watts without a heat sink. So let's see how this works on an example. Let's assume we have a 9-volt transformer that is used to feed a full wave rectifier with a filter and a 5-volt regulator. The average DC output of the filter is 9.5 volts. Calculate the power in the regulator and the load with a current of 1 amp. So like we saw on the previous slide, the power on the regulator is going to be 9.5 minus 5. So the input voltage minus the output voltage times 1 amp times the output current. And that is going to be 4.5 watts. And the power delivered to the load is going to be 5 volts times 1 amp, which equals 5 watts. So if you have a look at this, we are delivering, or the rectifier and the transformer are delivering a total of 9.5 watts, and we're wasting 4.5 in the regulator and delivering only 5 to the load, okay? So we're wasting in the regulator almost the same amount of power that we are delivering to the load. If we calculate the efficiency as the power delivered to the load divided by the total power delivered by the transformer, we end up with a 52% efficiency, okay? So from a power efficiency point of view, these regulators are not very good, okay? We'll get back to this. Let's take some special considerations here. One of them is voltage drop, right? We said that the 7805 that outputs 5 volts to the load requires at least 7.5 volts at the input. There's some other voltage regulators that are more modern than the 7805 that are called LDO. This is low dropout voltage regulator. So that means that the voltage drop across the regulator can be much lower. And modern LDOs can have voltage drops as low as 0.25 volts. Compare these to 2.5 volts for a 7805, and that is a much lower voltage drop, okay? So this is very well suited to battery operated devices, right? So you cannot afford probably to raise your battery voltage by an extra 2.5 volts. If you're using 1.5 volt batteries, that means you have to put 2 extra batteries just to compensate for the voltage drop on the regulator, okay? The other point that is maybe more important, or it is as important but not as obvious, is the quiescent current, IQ. This is the current through the ground terminal when no current is delivered to the load, okay? When we calculated the power example, we said that the current through the ground terminal could be a few milliamps, okay? And again, that is wasted power, even if the current through the load is pretty much zero. A 7805 is going to be just wasting 6 milliamps going through their ground terminal. Fortunately, again, more modern regulators exist that have a much lower IQ. So if you are designing a battery operated device, IQ is a parameter that you should watch very closely. There are some voltage regulators that have IQs in the range of a few microamps. So that's about like maybe 1,000 times lower than 7805, okay? So to summarize what we saw in this class, we saw fixed linear voltage regulators have very good performance. They're super easy to use. You just pretty much connected those between your unregulated input and connect that to the load that you want to use, and that's it. They're not very efficient from a power point of view, especially at high output currents, and you can easily waste 50% of the input power. If you're going to be designing a battery operated circuit, make sure you select an LDO, a low dropout voltage regulator, and one that also has a low IQ or a low quiescent current, okay? And if all these fails, you can also go to switching regulators, which is something that we're gonna be studying in a couple of classes from today. All right, so that's all for today. I hope you learned about voltage regulators, how to use them, and how to keep in mind some parameters that you have to watch closely depending on your application. We'll see you next class.